Greetings! I hope you're ready to learn about AVRDude and how to set fuse bits, because that's what we're doing today. The entire goal for this video is to take the circuit that we had before, where we had a bare bones example that used just a crystal oscillator and a blinking LED, and we're going to try to strip it down a little bit more to take advantage of some of the hardware that's built into the ATMEGA328. So we have the crystal and two capacitors there, which give us a system clock. And there's actually a built-in 8 megahertz system clock on the chip itself. But in order to configure that, you have to set fuse bits. So the purpose of today's video is to be able to remove the external components and use the internal stuff instead. In order to do that though, it does rely on the last video, which is how you're able to program an ATMEGA328 directly from a programmer or to use another Arduino as an ICSP programmer. That is how we will be flashing these fuse bits. Fuses are how we configure the microcontroller. In the ATMEGA328, we have a low fuse, high fuse, extended fuse, and while it's not technically a fuse, we have the lock bits. Not all microcontrollers use fuse bits to configure themselves, but this is what the ATMEGA328 and other AVR microcontrollers do. When you buy an ATMEGA328, the factory default has the L fuse set to 0110 0010. However, if you were to grab an Arduino Uno and pull the chip off of it and check what the fuse setting is for that, the low fuse would be all ones. So one of the questions is, why are they different and why do these particular bits matter? To answer that, let's walk through each section and see what it does to the microcontroller. One quick note is that a 0 means that a bit is enabled. So when you see something set to 0, that means that it's on, whereas something that's 1 is disabled or off. The first setting that we're going to look at is the clock divider, which is bit number 7. If this is enabled or set to 0, then whatever your incoming clock signal is will end up getting divided by 8. So by default, the ATMEGA328 uses an internal 8 megahertz clock. Then, with this bit being 0, it gets divided down to 1 megahertz. This means that your code with this setting would run roughly 1/16 of the speed of what the Arduino Uno has by default. The next setting is bit number 6, which is the clock out signal. This will take whatever the internal system clock is and re-emit it on a specific pin, and that's documented on the datasheet for the pin out. This bit is set to 1 or off by default. It's particularly useful if you're trying to run multiple microcontrollers or maybe a couple of ICs and you just want to use one clock signal for all of them. The next setting is the startup time, and what this does is it controls how long your ATMEGA will wait before it starts actually executing your code. And the reason that this exists is because when you power it on for the first time, it's not guaranteed that you're going to have a nice steady power source. So what this does is as soon as it gets power, it's going to wait a little bit for that to stabilize and then begin executing your code. The table describing all of the wait cycles are all in the datasheet, and if you want to mess with this, I would suggest looking there. And finally, the section that we really care about is the clock selection chunk. This allows us to do things like tell the microcontroller to use an external crystal oscillator or maybe use the built-in 8 megahertz oscillator. I want to draw some attention to the table right over here, where I have two numbers highlighted. The first one is what the Arduino default is, and you can see that that is a low power crystal oscillator, meaning that it's telling the microcontroller to use an external oscillator, whereas the factory default uses a calibrated internal RC oscillator, and that tells it to use the internal 8 megahertz oscillator. More details on all the possible combinations that you can do is detailed in section 8 of the datasheet, so look there if you're looking for something complex, but I usually just switch back and forth between these two. Before today, I had actually never looked at the fuse bits in the datasheet itself. I always use this online calculator, which I have linked up at the top, and there's tons of different online calculators that you can pick from if you don't like this one. But really, what they try to do is make it easier to understand what you can do to configure the microcontroller, and then they do all of the math and set the bits behind the scenes. I want to touch very briefly on what this looks like. It's mostly just checkboxes that have human readable text next to them, like the divide clock by 8 internally. We can decide if we want to do that or not. Sometimes it's not quite so simple, like this drop down here to pick our clock signal. You can see that this changes the clock selection bits as well as the startup time bits, so because of that there are a lot of options. You can read through them if you want to. It also shows all the stuff for the high bits, the extended bits, and lock bits. And finally at the very end it gives you a nice graphical understanding of what bits are on and off, and then it shows you what the configuration for that is in hexadecimal. Since our goal today is to make this run without the external oscillator, we want to use an internal 8 MHz crystal oscillator. And from the previous slide, the setting to do that is to set the clock select bits to 0010. We'll leave everything else the default how it is on Arduino, so that way we're not changing too much. As you can see here, we have the number in binary, but we can also represent that in hexadecimal, and that would be 0xF2 in this example. Also, if you're curious, most calculators that come on a computer have a programmer mode. I know that they have it on Windows and Mac, and the way that you can enable it on a Mac is to go to the View drop-down and switch to programmer mode, where you can see everything in binary, or you can go from hexadecimal to decimal to octal even. So, for example, if I wanted to know what this binary number is in hex, I can select the hex version and then just click on these little bits here to go 1, 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, and that tells me that this is F2 in hex. We've officially decided what we want to set our low fuse to in order to use the internal clock, but now the question is, how do we set that fuse? Enter AVRDude. AVRDude is a program that has a very intuitive acronym that stands for AVR Downloader and Upload. I'm not kidding, that's actually what it is. So if you look on their website, they have it documented there. AVRDude is the program that knows how to talk to your programmer, which will then flash the memory on your microcontroller. You don't have to use AVRDude. There's a couple other software packages out there that does the same thing. However, this is the one that's packaged with the Arduino IDE, so that's what I'm going to be using. I'm going to use the same hookup that I did for the last video, which is using an ICSP programmer to program the flash memory on the ATMEGA328 directly. In order to do that, I've got these 6 convenient pins that plug into the back of the Arduino Uno board, which are the ICSP pins. And then I give USB power to turn everything on. Just a reminder that if you don't have one of these devices, you are able to use a different Arduino as an ICSP programmer, and I cover that in my previous video. Now that we've got everything hooked up, let's push a program onto it by going to Sketch and Upload using Programmer. But this time we're going to focus on the output that's showing up down here, and this is all here because I have verbose output enabled, and I show you how to do that in the previous video as well. We're going to scroll up to the very first chunk of code here. What it does is it executes this line, and I'm going to copy paste this and we'll break it down. Alright, so this is pretty unreadable as it is, so let's try to clean it up a bit. The first thing that I'm doing here is splitting it up into the program that's being run and then all of the arguments. But even this is kind of unreadable because it's got those really long path names in there. So for now, I'm going to even strip those out. And this is what we're left with. So let's step through this. The very first thing we have is the command AVRDude, which is what the program is that we're running. The next thing is how we specify the configuration. So you type in -C and then pass in the configuration file. That contains things like the identification code of each microcontroller as well as any other settings that it needs to program it. -V is completely optional. It means verbose, and it will print out more information to the console rather than less, so that way you can debug if something goes wrong. The next one is -P, which is how we specify the part. Now this is required. This tells the AVRDude what type of microcontroller we're trying to program. The next line tells us what kind of programmer we're using, and in my case I'm using a USB Tiny, but if you're using an Arduino as ISP, you would have something different for this line. I'm going to cover all of that at the very end of this video, how to do everything all over using an Arduino as ISP. The last line that we have is the operation that we want to perform, and this isn't very easy to look at, so we can break this down further. The way that it's broken down to is you have the -U flag, which is the argument for AVRDude, and then we have all this information that's separated by colons. We have the mem type, the operation, the file name, and optionally the format. The mem type is where we specify what we are trying to program. The ones that I use are LFuse for the low fuse, HFuse for high fuse, eFuse and lock, as well as EEPROM, and then flash if you're actually trying to write your program to it. There's 9 other options, but I've never used those before. The next part is the operation that we want to perform. We have R, W, and V, which are for read, write, and verify, respectively. If we're trying to set a fuse bit, we would use W to write to it. Up next, we have the file name, which is essentially a path to a file if we're trying to push a program onto it. But when you're setting a fuse bit, we just hard code a number. And that brings us to the format. So the format is where you specify what type of format your data is in. I've only ever used I and M before. I represents Intel hex format, which is the output that Arduino compiler puts everything in. And then M is used for an immediate value, and you use this when you're not giving it a file name, but rather you're just hard coding whatever number you want to use. So I use I when I'm pushing code onto the microcontroller, and I'm using M when I'm trying to set a fuse bit. Using this information, we know exactly what we need to do in order to set the low fuse. We specify the -U for executing an operation. Then we specify LFuse as the mem type. We want to write to it, so we pass in a W. And then we hard code the value that we want to write into the low fuse, which is 0xF2 in hex. That last chunk M tells it that this 0xF2 is not a file, so don't try to open it as a file, but it's rather an immediate number. We hard coded the value. There are two files that really matter. One is AVRDude itself, the program that we want to run. But also we have to specify a configuration file. So if you download this directly from their website, you don't have to say the configuration file because it has a default, but the one that's packaged with Arduino doesn't have the default configuration saved in the right place, so we always have to point to it and say, I want to use this configuration file. So in order to run this, we have to first jump into the directory that the AVRDude program is in. So I'm going to do this since I'm on a Mac. I have to type in CD, which is change directory. It's the same on Windows. And I'm going to go to /applications, Arduino, contents, Java, hardware, tools. By the way, I'm hitting tab to autocomplete. This works on Windows and Mac and Linux. AVR bin, and hit enter then. Now, if you want to see the contents of a folder, on Mac and Linux, you type in ls, and on Windows, you type in dir, D-I-R. And in here, we should see a program called AVRDude, or AVRDude.exe on Windows. Now, just to test that everything works, we can run AVRDude without any arguments. And the way that you do that on Mac or Linux is to type in /, which means run a program from this current directory, and then AVRDude. On Windows, you just type in AVRDude.exe. We'll hit enter, and if everything goes well, it should print this help information. It's telling us, hey, you need some parameters in order to run this. Try these ones out. Now, we've already said that our goal is to program the low fuse, so we're going to go ahead and do that. We're going to start the program by typing in /AVRDude, which would just be AVRDude.exe on Windows. And we have to specify the path to the configuration file. So now this is back1 directory, and then inside of that is a directory called etc, and then that's where the file lives. So I can do that by typing in -C for the configuration path, // which means go back a directory, etc because it's in the etc directory, and then avrdude.conf. Hit tab to autocomplete to make sure it's there. I'm not going to do -V, I don't care about verbose settings. I do need to specify -P as ATMEGA328 because that is the microcontroller we're trying to program. And now -C to specify our programmer, which is USB tiny. And then we're going to do the meat of our command, which is -U for an operation. We want to program the L fuse. We want to write to it. We want to specifically set it to 0xF2, and that is an immediate, so we specify M, and let's see what happens. Boom. All right, so what's going on here? If I scroll near the top, we can look through right off the bat. It asks the microcontroller, it says, hey, what are you? And the microcontroller says, oh, I'm a 1E950F. And somewhere in that configuration file, it goes, oh, well, that's a ATMEGA328P. So then it writes the data of the fuse to it, and it sets it equal to F2, and then verifies it. It reads it back, and it says, hey, I just told you to be F2. Are you still F2? And then it says, yes, I'm still F2, and that means that everything is good. It's very happy, and it even prints off the rest of our fuse bits at the bottom. Now let's upload code using AVRDude. In order for that to happen, we first have to have a compiled version of our code, and we can tell Arduino to do that by going to Sketch, Export Compiled Binary. So that will compile the code and save it as a .hex file. This is my Blink example, so you have to go to where your blink.ini file is saved. On my computer, that is in my Documents folder, and then inside of Documents is Arduino. Inside of Arduino is Blink. And here we see the blink.ino, which is our source code, but then we have two hex files, which is standard.hex and one that has a bootloader built in. If you right-click on a file and hit the Option key on a Mac, you'll have a chance to copy it as a path name. You can do this with Windows by holding Shift before right-clicking, and it will copy it as a path name. And then when you go to paste that in to your terminal, I'm going to hit up to go back to my previous command in here. Instead of lfuse, we're going to type in flash, and then we want to write to our flash, and then we're going to specify this file. So now I can paste in that thing that I just copied, which is a path to my user folder, documents, Arduino, Blink, and then my hex file. And then I type in :I to specify the format, and we're telling it, hey, this is an Intel hex format. So now if I hit enter, that should push our code. It writes, reads, and everything is done. So now our microcontroller has the Blink example saved onto it. I want to touch on one thing that tripped me up a while ago. Sometimes your project name might have a space in it, so like maybe my project name isn't Blink, but it's Blink Light or something like that. The way that it interprets a command is anywhere where it sees a space, it interprets that as the next argument, which means that this section right here where we have our flash, it would read all the way up to here as our path, and then it would think everything after it is a separate command. So if that ever happens and you have a space either in your file path or in your project name, just go back to the very beginning of the parameter here where we have -u and put quotes around this whole thing. So I'm going to put that there, and we're going to put quotes at the very end as well. And then when you execute it, it will treat it as one giant file name. Now it's time to test to see if this works. So we're going to disconnect our programmer from our Arduino Uno here. We're going to take this chip off, so don't break any more pins. I'm going to bring up our circuit here, there. And now we're going to remove our crystal oscillator. So I'll pry that up with, and also the capacitors. We shouldn't need those either. So now if everything works right, as soon as we give this power, we should see that that light will still blink because we're using an internal oscillator instead of an external one. Hey, it looks like everything is working. So one thing to note is that this is now running at half the speed that it was before. Instead of it blinking on and off once per second, it's now doing it once every other second. And the reason for that is because the way that the Arduino delay function works is by counting clock cycles. It literally wastes a preset amount of clock cycles. Now that we slowed down our clock, that means that each clock cycle is twice as long. So it's still waiting the same amount of clock cycles, it just relates to a different amount of time in real life. Now I promised you I'd show you how to do everything with an Arduino instead of an ICSP programmer, so I'm going to fly through that real quick. I'm assuming that you already know how to wire everything up from the previous video, so let's jump into it. First thing we need to do is to make sure that our programmer is switched over to Arduino as ISP. The next thing we have to do is make sure our port is pointing to the right Arduino on our right COM port. After that's all done, we can do a test upload sketch here to get a sample of what our code should look like. So upload using programmer, scroll up to the top, and copy this line of code. Enhance. Enhance. This looks pretty similar to what we had before. We still have our AVRDude. We have to pass in a config path. We've got our verbose. Our part is still the same, but this is where things differ. We've got our programmer type is now an STK500V1, and the only reason for that is because whoever wrote the code for the Arduino, they made it emulate something called the STK500. It talks to the Arduino over serial, so we have to tell it what port it is. Mine looks like this on a Mac, but yours will say something like COM11 or something like that on Windows. We have to tell it what speed we are talking to it over serial as well, so we have to pass in a baud rate, which is 19200 when you're using the Arduino as ISP default code. And then the operation is exactly the same. So let's do it. So we got AVRDude, we got our configuration path is //etc/avRdude.conf. -P is our ATMEGA328 -C is our STK500V1. Our port -P is, in my case, /dev cu.usb modem. Our baud rate -B is 19200, and -U, we're just going to set the fuse bit here, so that'd be LFUSE for our low fuse. We want to write a value of 0xF2 to it, and that is an immediate. And that is how you do it with an Arduino as ISP. Alright, that wraps up today's video. That was a lot of stuff that we've covered. We're getting very close to wrapping up all of the fundamentals for a microcontroller. So I'm kind of curious what you guys want to learn about next. So my big three that I'm thinking of off the top of my head are jumping into compilers and seeing how you compile code without using Arduino at all. Alternatively, we know enough that we could ditch the ATMEGA328 and try a new microcontroller, so something like the AT85, and then after we get familiar with that, we could jump into an STM microcontroller. Or alternatively, we could dig more into the code and try to find something like an analog to digital converter, like an analog read, or maybe do UART without any libraries at all, so just following the datasheet. Whatever interests you the most, let me know in the comments, and I'll see you next time.